for Unit 6, Day 10, and they start on 2080 or page 2080 of your packet. And we're looking at an integrated integration technique called substitution. So the essential question is still the same. How can I incorporate what I know about derivatives to find antiderivatives? So we know the antiderivative process is just running those derivative rules backwards, starting with your rate of change, accumulating that underneath between the rate of change and the horizontal axis. And when we do that, we end up with the function we started with before we differentiated and found a rate of change. So that's kind of the terminology we were accustomed to using during the first portion of the unit. Now what we're basically doing is we're boiling down that verbiage and saying, I may have a definite integral or an integral, and I would like to find the antiderivative. So we went through some basic rules, went through all the basic differentiation rules to see how they would work to see how we would use them when we were finding antiderivatives. And now we're going to get to some of the more complex ones, and the more complex ones involve substitution. So here is the Webster Dictionary's definition of substitution, which I'm not really sure I had to show you, but the idea is that, just kind of like when you have a substitute in class, you're replacing someone or something with another person or thing. So you see this all the time when you come to school and you have a substitute in your classroom. And we are going to physically do this also in some of the more complicated antiderivative questions. So for instance, when we look at this, finding this antiderivative, 3 times the quantity 5x plus 2 to the 20th power. Now, if that were just to the second power, we could FOIL it out. But to the 20th power, I'm not sure we want to do that. It's possible, and then we could just use the power rule. But the idea here is, instead of spending all of that time foiling, we could look at this more like a composite function, right? We could look at this as 3 times something to the 20th, where the something is itself a function. So it is literally a composite expression. And you know that when you have a composite expression and you're differentiating, that we need to use the chain rule. So use substitution is literally the chain rule in reverse, right? Because we're really focusing on reversing our differentiation rules. And so this is no different. We're reversing our differentiation rule here. We're reversing our chain rule. So the first thing we do is, and in doing so, we're also going to reverse the power rule. In doing so, we are going to take this and kind of pose this question here. Wouldn't it be easier if we solved this expression? So the antiderivative of u the 20th, then we can literally just reverse the power rule. And so that's the direction we're going to go in then, is that we're going to take this out. We're going to kind of rip out the inner function of the composite expression and call it a u. And then we're going to go ahead and adjust this so it can look sort of like this. And I say sort of because we've got a 3 we have to consider here, and some other things. We've got a dx here, and now it's a du, and we don't know the relationship between dx and du. So, but we definitely wanted something as simple as this, so we can use a very basic antiderivative process. Okay, so let's go back. So we have this. That's what we physically have as our question. I put the 3 out front because we can do that with constants. That's just a coefficient. And then I'm going to focus on that. So I'm going to go ahead and do this substitution. Let u equals 5x plus 2. So we're going to put a u right here. But the problem is if we put a u here, then this differential has to be in terms of u as well. And so the way we get that connection is we go back to this inner function and we say, well, I can differentiate that. That's pretty straightforward. And now I have a dx and a du, and I can substitute out the dx just like I substituted out the 5x plus 2. So this is how we do this. We rearrange this differential, and we go ahead and cross multiply, so to speak, right? Because this is 5 over 1. So it's du times 1 equals 5 times dx. We can do that cross multiply process with our differential expression. So we get this. And so we're getting close. We need the dx. So in order to get the dx by itself, we're going to divide by 5. So the dx is then du divided by 5, or 1/5 du. So if you think about it, just mathematically thinking about these 3 steps, we started with the derivative, and all we really did is swap the 5 and the dx, right? That's the cross multiply and divide process. So if you can get comfortable with just taking this and just swapping them, you can skip that intermediate step. Okay, so let's put this together then. So this is where the substitution takes place. Here's our original expression. Everything up here is what was on the previous screen and this. So here's the original expression. We're going to take out the 5x plus 2, and we're going to put in the u. We're going to take out the dx and put in the du over 5, the 1/5 du. So let's take a look at this. So from a composite standpoint, you remember the derivative is the differentiating the outer function and evaluating it at the inside times the derivative of the inside. So this is the reversal of that process. Instead of multiplying by the inside derivative, we are dividing by the inside derivative, right? This is the inside. This is the derivative of the inside. We're doing a division process. We're reversing that chain rule. Okay, so this is just 1/5 du. So I'm going to factor out the 1/5 and stick it with the 3. So I got 3 over 5. Now I have something that is a basic reversal of the power rule. So we have 3/5 times u, bump up the power by 1 to the 21, divide by 21. So there's our power rule. And let's simplify this a little bit. 3 and 21 can be reduced to 1 over 7. So it looks like we have 1 over 35, u to the 21. And we're almost done. We know we started out in terms of x, and we need to end up in terms of x. So we need to substitute again, get the u out, and put back our original expression. So it's 1 over 35, 5x plus 2 to the 21. And then, I forgot something pretty critical here. So let me do that. And don't forget that. Hopefully this will solidify that. Don't forget that plus c on the end. There we go. So we definitely need that plus c on the end to complete the antiderivative process. So hopefully, hopefully me stopping the presentation and putting that correction in will help you remember that, to do that on each antiderivative question. Okay, so let's formally look at what's going on here. So typically substitution involves finding a pattern that looks like this, a nested function and its derivative. Now the one we just got done doing did not have, they had the nested function, but it didn't have the derivative out here. Remember, the derivative was 5. We didn't have that. And that is one of the scenarios where that's okay, because the derivative is just a numeric constant and it comes out anyway. I'll show you some examples that follow this pattern quite literally, where we have a composite, and then out here we have the derivative of the inside, because this is the chain rule right here, right? We got the derivative of the, remember, this is the derivative of the original function, right? So we've got the derivative of the outside evaluated at the inside times the derivative of the inside. And so our substitution that's involved is doing that u substitution and manipulating the differentials, manipulating the derivative of the inside, so to speak, to get that du expression. Now, if we had a definite integral, we also would have to change the bounds to get those in terms of u as well. We're going to do an example like that a little later in the notes. So here are, we didn't go through them formally, but here are 7 steps that we can follow to kind of navigate this process. So we're gonna follow these 7 steps pretty closely from here on in. So remember this nested function, we call that nested function a composite. Okay, so we're going to look for the function and its derivative. We're going to look for that pattern. Example 1 that we just got done doing, it was kind of tricky because we didn't see this pattern because the derivative was a numeric constant. And example 2 is going to be a tricky one as well. So let's take a look at example 2. So we need to look for that function and its derivative pattern. But in this antiderivative question, we just have tangent and 3x. And so if you think about, well, which one's the function, which one's the derivative, it doesn't make sense because neither are the derivative of the other one. So this one is a tricky one. Again, we don't see a function and its derivative. I see a function tangent, and certainly the inside is 3x of the composite, but I don't really see a derivative of a tangent. So what we want to do then is we want to think about, well, how can I rewrite this to get that pattern? And the way we can rewrite tangent, since we don't have that pattern, is we can rewrite it as sine over cosine. So if I rewrite it sine over cosine, then I have a function cosine and its derivative sine, or vice versa, because we know that we can kind of work those trig functions either way. So the question is, well, which way do we do this? Is the function sine or is the function cosine? And so a rule of thumb here is if you have a rational function, make the bottom u, and then the top will end up being the derivative. So it just ends up being an easier integration when we do that. So that's what we're going to do. We're going to say u is cosine 3x. We're going to differentiate that. So du dx is the derivative of cosine is minus sine 3x. But then we actually have a chain rule in here. Now this is just straight up differentiation. So we need to do the chain rule when we are doing the derivative here. So it's -3 sine 3x. So the negative comes from differentiating cosine. The 3 comes from differentiating the inner function here, 3x. Okay, so now we need to rearrange that. So I'm just going to do I call this the switcheroo. I know I need to solve for dx, so I'm going to stick dx over here. I'm going to stick everything over here down on the bottom. Okay, so that's the cross multiply and divide. So dx is this big complicated thing. Now, you might look at this and think, it doesn't seem to make anything any easier, but watch the canceling that occurs when we do the substitution. Okay, so I'm going to color code things here. I am going to substitute cosine 3x, I'm going to substitute in u, and I'm going to substitute in this messy thing for dx. And I know it doesn't look like it's going to get simpler, but just kind of watch what pans out here. So this is a u. I have this whole big complicated thing here, and we have some canceling occurring. So this is what will happen all the time. When we do the substitution, if there is any expression that still has an x in it, this substitution, finding the derivative and substituting out the dx, will take care of any remaining x expressions. So we can cancel the sign of 3x top and bottom. We have a -1/3 here. And so we're going to put the -1/3 out front of the integration. And then we have 1 over u du, right? This u is in the denominator. Make sure it stays in the denominator. So now we're left to do the antiderivative of 1 over u, which is much simpler than this. We know that the antiderivative of 1 over u, if you look at your derivative flip books, that is reversing the natural log. So we're going to integrate that. The antiderivative of 1 over u is the natural log of u. And then now we can substitute back in. So we can go ahead and put back in our substitution of cosine 3x and put our plus c on the end. And this is the antiderivative of the tangent of 3x. Okay, let's take a look at example 3. So example 3, you might be able to see the u substitution, the function and its derivative sort of a little more obviously, but it's still pretty tricky. So a general rule of thumb here, like the last time, the trig problem, we had to rewrite the tangent, and then we got this rational expression, and the general rule of thumb is when you have a rational expression, the u is in the bottom. We can kind of say the same thing here, but we also have an exponential here, and exponentials kind of are a higher priority than irrational expressions. So exponentials, we're going to make the power u. And these are things that you just have to kind of keep in mind as you practice these problems. They're like little tricks. And so, but think about this. This is also the denominator. Now, the tricky thing here is that if we call u the square root of x, then this is e to the u. And we have to look at this in the denominator as a derivative, because it's really 1 over the square root of x. And that is the derivative of the square root of x. Remember, we do a power rule on this. Let's differentiate this. This is x to the half power. We bring down the half. We reduce the power by 1. And if we rewrite this, we end up with a square root in the denominator. So that is exactly what we have here. So this is actually the derivative, and this is actually the function. This derivative form here is because we have a 1 in the numerator and a root x in the denominator. 1 in the numerator, root x in the denominator. We have to bring this 2 through, but watch what happens as we do. Okay, so we have this. I'm just getting rid of this middle stuff. Now I'm going to cross multiply. So we got dx times 1 equals 2 root x du. So this is what's going to go in for dx. So let's do that substitution here. So for this u, I'm going to put it up here for root x. I'm going to leave this alone because I'm going to substitute this in for dx, 2 root x du, and the root x's will cancel. So let's take a look at what that looks like. So that substitution then looks like this. So we have e to the u, and then we still have the root x in the bottom. We're not moving that. And then the dx is going to be 2 times root x du. And then we're going to be able to cancel the root x's. And this 2 is in the numerator, right? This is all in the numerator. This 2 is going to come out front. And then we're going to have e to the u du. And when we integrate e to the u du, we get 2e to the u. Remember, e to the u is its own derivative, so it must be its own antiderivative. And this came up a little before we needed it. And then we're going to go ahead and rewrite it and substitute back in the square root of x. So this antiderivative is 2e to the root x plus c. So if we think about differentiating this, if we differentiate this to kind of check our work here, the derivative of 2e to the root x is 2e to the root x times the derivative of root x. So if you think about this times this, right, because e is its own derivative, see how the 2's cancel? And then we end up with the root x back in the denominator. And of course, differentiating a constant of integration, this would be 0. Because remember, this is just a number. We get that because we can have any y-intercept. This is a family of functions. Okay, so you can stop the video and try this one on your own. Again, it's an exponential, so make the power u. So go ahead and stop the video and try to do this one on your own. Okay, if you're joining me back, hopefully you made it through up through step 6. Okay, try steps 1 through 6. Try not to do step 7 because we do have a definite integral here. So let's go through this. So our u is our power, 4x squared minus 1. We can see that this is a form of the derivative. When we differentiate 4x squared, we get 8x. And so we have an x here and an x here, and the coefficients don't match, and that's okay. That just means we get some coefficients outside. But we have matching powers of x here, and that's so this is the derivative. So we look at 3x as kind of like a form of the derivative. It's got the right power of x, and that's what the important thing is. The numbers, the coefficients, excuse me, the coefficients will work themselves out. Okay, so let's solve for dx. So I'm going to do that swapping. We put the 8x down here and the dx up there. That's the cross multiply and divide. And now I'm going to go ahead and do my substituting. So this goes in for, u goes in for 4x squared minus 1. Du over 8x goes in for dx. So now the integral looks like this. It looks like 3x e to the u times du over 8x. And if you notice, I got rid of the upper and lower bounds. These upper and lower bounds refer to doing an antiderivative in terms of x. And we are no longer going to be in terms of the variable x. So these upper and lower bounds are no longer going to be 0 and 3. We got to figure out what those are. So what I do is I just leave them off until I do all of the anti-differentiation, and then I put them on at the end. Okay, so let's go ahead and cancel. So the x's here are canceled, and we end up with 3 over 8. So we're going to put that out front, and we're taking the antiderivative of e to the u du. And we know that the antiderivative of e to the u du is itself. So we got 3/8 e to the u. And now we've got to evaluate this. This would be the antiderivative if we put plus c on the end, but we have a definite integral. So now we got to bring back in the lower and the upper bounds. So the upper bound is 3, and I've got to put it in here because that's in terms of x. So 4 times 3 squared minus 1 is 35. Excuse me. So so use the upper bound in terms of u is 35. And then I've got to do the same thing for 0. I've got to put it up into here to get it in terms of u. So we have 4 times 0 squared minus 1 is negative 1. So that's the lower bound. So we're going to evaluate this from negative 1 to 35. So it's going to look like that. So the value of the definite integral here then is 3/8 e to the 35 minus e to the negative 1. And we just leave it like that. We don't try to evaluate that without a calculator. So that would be the value of the definite integral. So the last one then is example 5, and it's rational. And again, with rational, the rule of thumb is make the bottom u. So the bottom, if the bottom is going to be u, then where your substitution is going to be 3x plus 1. So go ahead and stop the video and try to do this one all the way through, even step 7, even rewriting the lower and the upper bounds and evaluating the limit, or evaluating the integral, excuse me. So go ahead and try that, stop the video and try that on your own. Okay, if you're coming back now, I'm assuming you've tried this u sub on, or this integration and u sub on your own. So let's go through the steps here. Step 2 is to differentiate your u, so your du dx is 3. Step 3 is to solve for dx. So with this one, we can just do the swapping. So it's du over 3 equals dx. Step 4 is to do the substitution for the u and the dx. So we are going to have the, and I'm going to get rid of the limits of integration right now because we're transforming this to a u problem instead of an x problem. So we get 2 over u times du over 3. So we have a coefficient of 2/3 we're going to put out front. There is no canceling because this derivative is numeric. And when the derivative is numeric, the only thing that happens is the coefficients change. So there's no canceling that we need to do. So we are integrating 2/3 is out front, 1 over u du, and we integrated this already in this note session. We know this is natural log of the absolute value of u. So this is 2/3 the natural log of the absolute value of u. And then now we need to get our lower and our upper bounds in terms of u. So if x equals 5, and I put 5 into here, I get 3 times 5 plus 1, which is 16. And if x is equal to 1, I put 1 into here, and we get 3 times 1 plus 1, which is 4. Right? 3 times 1 is 3, plus 1 is 4. So our new bounds for evaluation of this antiderivative is 16 and 4. So we're going to evaluate that. And so that means we're going to stick in 16 and stick in 4. And so it looks like this. And if this were a free response question, this is an answer, an algebraic answer, you would just leave it alone and move on. If this were a multiple choice question, the answer is probably not going to be in this form. So I'm going to go over what we can do for natural log, re-expressing the natural log to rewrite this expression. So these are logarithmic properties that you may remember, you may not, but we need to kind of dust off the cobwebs and figure these out. Okay, so remember that when we have a natural log of a number minus a natural log of a number, that we can rewrite that as a quotient. If there was a plus here, we could rewrite it as a product. So keep that in mind. And then 16 divided by 4, we can simplify that. That's a natural log of 4. In addition, 4 is a perfect square, so we can rewrite this as natural log of 2 squared. And that's important because a power can come out front. Okay, natural log is really counting by powers. So powers can come out front. So this can be rewritten as 2/3 times 2 times natural log of 2. Well, we can simplify this. That's really 4/3. So 4/3 natural log of 2 is probably the answer you're going to see on a multiple choice question, even though you got this. So you have to recognize those logarithmic properties so that you can rewrite this to figure out which one is the rewritten correct answer. All right, when we get back into the classroom, we'll go over some more use substitution and refine our skills with a variety of problems.